Welcome back to Harryverse. Thank you so much for tuning in to another deep dive into the strange and beautiful side of our universe. Today we are breaking down a real interstellar mystery, the Comet 3I Atlas, and its surprising load of prebiotic molecules. If you enjoy these science fiction-style news reports about cosmic discoveries, please hit like, subscribe, and share this video with a friend who loves space as much as you do. It really helps Harryverse grow. And I would love to know what time is it for you right now, and where in the world are you watching from? Tell me in the comments below, and let's see how far this signal from Harryverse is traveling tonight. Astronomers do not expect the alert that appears on their screens when the object that will be named 3I Atlas first enters the shared databases of the world's sky surveys. At first, it looks like many other faint, slowly brightening points recorded in the outer reaches beyond the orbits of the giant planets. Automated software flags its changing position night after night, and observatories in different countries refine the track. The early motions suggest a long-period comet falling inward from some distant cloud of icy bodies surrounding the solar system. Nothing about that is unusual. What changes the story is the way the path refuses to curve the way a bound object should. As more measurements come in, the calculated orbit stretches and opens until the line that best fits the data is not a closed loop, but an open branch that never turns back. The computed eccentricity, a simple number describing how stretched an orbit is, climbs past the values typical of long-period comets and stays there. In plain terms, the object is moving too fast and on too open a path to be trapped by the gravity of the sun. Analysts repeat the fits with different assumptions, checking for errors in the astrometry, looking for subtle biases in the early positions. The answer remains the same. The object arrives from far outside the planetary region, cuts through, and will leave again forever. The discovery teams inform the central offices that coordinate new solar system objects. Provisional designations are assigned, and work begins to compare this newcomer with the very small set of confirmed interstellar visitors that have passed through before. The first of those, known as 1I Oumuamua, was a dim, elongated body that barely released gas at all, leaving debate about its exact nature even today. The second 2I Borisov was more clearly a comet with a steady coma and tail, yet still displayed some differences from typical comets of the outer solar system. Now a third member joins this group, and from the outset it seems eager to show its own kind of strangeness. Follow-up telescopes across the world begin regular monitoring. A network of professional observatories and skilled amateurs tracks the brightness and color of the object as it falls inward. Color measurements in astronomy are simple comparisons between how bright something appears in one band of wavelengths and another. They can reveal whether a surface is dominated by fresh ice, dark dust, or complex organic rich material. For 3I Atlas, those early color indices drift toward the redder side, compared with the average solar system comet at a similar distance from the Sun. The difference is not extreme, but it is persistent across several independent data sets. Teams recheck their calibrations and compare with nearby stars to rule out instrumental effects. Once again, the signal remains. A slightly redder than usual interstellar comet hints that its surface has been processed under conditions that do not match the typical experience of comets stored in the outer reaches of the Sun's own cloud of icy remnants. Reports also note that the brightness of 3I Atlas rises a little faster than standard models would predict for a body of its estimated size and distance. Brightness is a mix of reflected sunlight from solid surfaces and scattered light from fine dust. If the change over time is steeper than expected, one explanation is that the comet is beginning to release dust and gas earlier in its inward journey than most. Another is that its surface is unusually efficient at reflecting light, perhaps due to a different texture or composition. Astronomers keep both possibilities in mind and wait for further data. The overall mood in the community is one of cautious excitement. Interstellar objects are rare, and each new one offers a brief chance to sample material formed around another star. Observers draw up plans to measure the coma, the thin atmosphere of gas and dust that can envelop an active comet, and to compare the chemical fingerprints of 3I Atlas with those of comets that formed around the Sun. Microwave and millimeter observatories are placed on high alert since the cold gases released by comets shine strongly at those wavelengths. Optical and infrared telescopes schedule repeated visits to catch changes in color, brightness, and structure. Space agencies take note as well. Although there is no existing spacecraft ready to intercept this sudden visitor mission, planners use the early orbit solutions to test how difficult a future rapid response mission would be. They find that the high speed and steep approach angle of 3I Atlas would make interception challenging with current launch vehicles. But the exercise is useful. It shows again that if humanity wishes to examine an interstellar object up close, it will need to prepare in advance. For now, all the work must be done from a distance. The news releases that begin to appear from major observatories and agencies frame the event carefully. They describe 3I Atlas as a rare interstellar comet, whose path confirms that it comes from beyond the solar system, and they note early hints that its color and activity do not entirely match the familiar patterns. At this stage, the story is still one of discovery and classification. Yet beneath the cautious language lies a simple fact. This object carries within it frozen material assembled in a different planetary nursery around another star, and it is now passing close enough for modern instruments to study. The stage is set for a detailed look at its chemistry, and with it, for the first clear sign that one particular molecule inside this alien comet will force scientists to rethink how common certain building blocks of complex chemistry may be among the stars. In conferences and online seminars, researchers begin to place 3I Atlas in context, contrasting it with long-period comets, with asteroids, and with the two earlier interstellar visitors. The consensus view is that even if nothing further is learned, its confirmed interstellar origin and mild peculiarities already expand the small sample of known planetary systems beyond the Sun, but many suspect that its real significance has yet to appear in the data. As the days pass and 3I Atlas moves inward, observers notice that its behavior begins to diverge more clearly from the standard script for long-period comets. At a distance where many comets remain quiet with surfaces still too cold for much activity, the interstellar visitor already shows signs of a forming coma. Photometric data, which track overall brightness, reveal a small but steady excess above what would be expected from sunlight, reflecting off a bare nucleus of the estimated size. At nearly the same time, high-resolution images from large ground-based telescopes start to show a faint diffuse glow surrounding the central point. This glow is the earliest stage of the gas and dust envelope that astronomers call the coma. For many well-studied comets that formed in the solar system, the onset of such activity usually occurs closer to the Sun, where heating is stronger. The fact that 3I Atlas begins to shed material farther out suggests that either its surface ices are unusually volatile, or its outer layers respond to heating in a different way. Teams that specialize in modeling cometary activity take notice. They apply standard thermal models that balance incoming sunlight re-radiated energy and the cooling effect of sublimating ice. These models have been refined over decades using data from numerous comets that loop in from the distant cloud of icy bodies surrounding the solar system. When the same tools are applied to 3I Atlas, the predicted level of early activity falls short of what is observed. To match the data, the models must assume that the surface is either richer in highly volatile ices that respond to weak heating, or that the insulating dust crust is thinner than usual, allowing subsurface ice to reach the temperature needed to vaporize more quickly. Both options are interesting, and neither fully satisfies the constraints from color and brightness measurements, which suggest a somewhat processed reddened surface that should be more, not less, insulating. Radio and infrared instruments join the effort. Sensitive spectrographs mounted on large telescopes monitor specific wavelength bands, where common comet gases such as water carbon monoxide and carbon dioxide emit or absorb light. At the large distance where 3I Atlas begins to stir water, ice is still cold and slow to sublimate, but carbon monoxide and carbon dioxide can already be active. Early spectra indeed hint at contributions from these more volatile components, but interpretation is complicated by the faintness of the signals and the overlap of lines. Still, the presence of even modest gas emission at this stage reinforces the impression that the comet is waking early. The early coma is not uniform. Time series images show that the brightness around the nucleus changes in a way that points to small jets or localized active patches turning on and off as the comet rotates. Models of the rotation period based on periodic variations in brightness suggest that the nucleus spins in many hours, not in minutes, but also not over several days. That range is common among comets, yet the pattern of activity for 3I Atlas seems unusually sensitive to changes in solar heating over a single rotation. This hints at a surface that is divided into regions with sharply different compositions or structures. Some areas might be covered by a thick radiation-darkened crust, while others expose fresher ice that responds quickly as it comes into sunlight. The early onset of activity also fits with ideas about long-term interstellar processing. Before entering the solar system, 3I Atlas likely spent tens or hundreds of millions of years traveling through the thin gas and dust between stars. In that environment, high-energy particles known as cosmic rays can slowly modify the outer layers of icy bodies, breaking molecular bonds and building new, more complex structures. Over time, this processing may produce a skin of chemically altered material above less modified ice. When such an object finally approaches a star, the processed skin can fragment or crack under thermal stress, exposing deeper layers and releasing gas in ways that differ from comets that have spent their history inside a protective cloud tied to a single star. Some researchers propose that this interstellar aging may have created internal stresses, microfractures, and pockets of trapped volatile gas within 3I Atlas. As the comet warms, these pockets might open in sudden bursts, producing jets and diffuse outflows at greater distances than expected. Others explore whether the unusual timing of the coma could mark the release of species that are rarely dominant in solar system comets, but might be common in other planetary systems. In this view, the early activity becomes a clue that the stored inventory of ices inside the nucleus is not the standard mix used in current models. Observational teams coordinate to watch for any signs that dust grains are being lifted from the surface and spread out into the young coma. Polarimetric measurements, which examine how light becomes polarized when scattered by dust, indicate that the grains have sizes and structures within the broad range known from other comets, but the emerging pattern is not yet clear. Some nights the coma appears slightly broader or more asymmetric than the simple ideal of a smooth spherical cloud. Careful processing reveals hints of narrow features that could be jets, but the resolution is near the limit of what the instruments and seeing conditions allow. This uncertainty keeps the discussion open. At the same time, agencies that operate space-based telescopes in infrared wavelengths consider how to use their limited time. Observing time on these facilities is highly competitive, and interstellar comets arrive without warning. The case for 3I Atlas is strengthened by its early outgassing, which promises a more extensive coma and richer spectra over a longer path near the Sun. Proposals emphasize that catching the comet at multiple distances from its first stirrings to peak activity will make it possible to track how different molecules switch on and off with changing temperature and radiation. That sequence, in turn, would reveal which ices are abundant and where they are stored inside the nucleus. Popular science outlets and specialist news services begin to pick up on the story of the unusual early coma. They describe an interstellar comet that seems to start shedding gas sooner than its local cousins, and they present this as a sign that it carries a different internal structure or mixture of ices. Editors reach for simple analogies, but scientists involved in the observations stress plain facts. This object is releasing gas earlier and at a greater distance than expected. The cause is not yet clear. Several possibilities exist, and they are all valuable to test because they probe conditions in another star's planetary system. In parallel, the team preparing for observations with the Atacama Large Millimeter Submillimeter Array watches the evolution of the coma with particular interest. For their instruments to build detailed maps of molecular emission, the comet must be active enough to produce detectable lines, but not so close to the Sun that it sets too quickly or becomes difficult to track in the sky. The early onset of gas release suggests that the window of useful observing time will be wider than first assumed. It also raises a question that will later become central. If the comet is already active this far out, how will its chemical profile develop as it moves closer? And will that profile match anything previously recorded for solar system comets? Or will it display a pattern that forces scientists to expand their understanding of cometary chemistry? By the end of this phase, the description of 3I Atlas in internal reports has shifted. It is no longer just a rare interstellar comet on a hyperbolic path. It is a body whose coma has turned on early, whose brightness changes hint at complex surface patches, and whose potential for revealing unusual chemistry grows with every new data point. The stage is now set for radio observatories to examine its gas in detail, and for one simple molecule in particular to move from supporting actor to central focus in the unfolding story. When the activity of 3I Atlas is clear and its path across the sky is well defined, the focus of the campaign shifts toward a type of observation that turns light into chemistry. Among the most powerful tools available is the Atacama Large Millimeter Submillimeter Array. In the Chilean desert, a collection of many dishes spread across a high plateau. Working together as a single instrument, these antennas can pick up the faint radio and millimeter signals emitted by cold gas in space. For comets, those signals come from molecules in the coma that rotate and vibrate in characteristic ways, producing a pattern of narrow lines at specific wavelengths. Each molecule leaves a recognizable fingerprint in the spectrum. By measuring the strengths and shapes of those lines, astronomers can identify which species are present and in what relative amounts. Time on this facility is valuable, and the proposal for 3I Atlas must compete with many other projects. What strengthens its case is the combination of its rare interstellar origin, its early outgassing, and the chance to compare its chemistry directly with that of comets born around the Sun. The argument is straightforward. If comets preserve samples of the ices and dust from which planets form, then an interstellar comet is a sample from another planetary system. Detecting even a small set of key molecules in its coma would offer a first direct comparison between the building blocks available in that distant environment and those in the early solar system. The review panels agree, and a series of observing blocks is scheduled for different points along the comet's inbound leg. When the first window opens, arrays of dishes swivel to point at a patch of sky that to the eye contains only a faint star-like point drifting among the background constellations. Receivers are tuned to cover bands where common cometary molecules leave their marks. These include water by way of its fragments, carbon monoxide, hydrogen cyanide, simple alcohols, and a handful of other species that experience has shown to be important in icy bodies. During each observing run, the array records raw data that engineers and specialists later turn into calibrated spectra and eventually into maps of emission around the nucleus. In parallel, smaller radio telescopes in other parts of the world also watch the comet at selected frequencies, providing cross-checks and filling in gaps. The story that begins to emerge from this combined effort is not one of absence, but of unexpected balance. Early spectra clearly show that 3I Atlas is a chemically active comet. Lines corresponding to several familiar molecules are present, and some are stronger than initial sensitivity estimates had promised. In that sense, the interstellar visitor behaves like a robust gas-rich comet rather than a marginally active fragment. Yet when the intensities of these lines are compared with one another using standard techniques to account for excitation conditions and beam size, the ratios do not sit comfortably within the ranges that decades of solar system studies have made familiar. In solar system, comets' hydrogen cyanide often tracks water in a roughly consistent proportion, varying by factors of a few, but tending to fall within a known band. In 3I Atlas, the hydrogen cyanide lines appear stronger relative to some other species than expected, as if the comet carries a somewhat elevated inventory of this simple nitrogen-bearing molecule. At the same time, features associated with methanol, a simple alcohol, stand out more clearly than usual. Those responsible for the data reduction run repeated checks. They verify that the line identifications are correct, that nearby unrelated sources are not contaminating the signal, and that calibration against standard sources has not introduced artificial boosts. The patterns remain. In some frequency ranges, methanol lines blend with others, making precise measurements difficult, but even conservative estimates suggest that this interstellar comet may host a higher fraction of methanol in its coma than typical solar system counterparts. The conclusion is not yet firm. More data are needed at different times, and careful modeling of the coma environment must be carried out to translate line strengths into abundances. Still, observers note in their internal reports that if current trends hold, 3I Atlas could belong to the class of methanol-rich comets, with the added twist that it formed around another star. A further layer of detail comes from the way the array can map where different molecules are located around the nucleus. Unlike a single dish which provides an average signal across its field of view, an interferometric array can reconstruct images of emission at high spatial resolution. For 3I Atlas, this means that astronomers can ask not only which molecules are present, but also how they are distributed within the coma. Early maps suggest that hydrogen cyanide emission is tightly concentrated near the central region associated with the nucleus, falling off steeply with distance. This pattern matches a picture in which hydrogen cyanide is released directly from ices at or just below the surface as they sublimate under solar heating. Methanol, however, seems more extended. Its emission does not drop as quickly with distance from the nucleus, and appears to fill a broader region of the coma. This could mean that methanol is being produced or liberated, not just at the surface, but also within the gas cloud itself perhaps, as sunlight breaks apart larger organic rich grains, or as chemical reactions proceed on the surfaces of tiny icy fragments. Another possibility is that the nucleus contains layers with different compositions, some richer in methanol-bearing ices than others, and that chunks from these layers are breaking free and releasing their content as they drift outward. Each of these scenarios implies a different internal history for the comet. For now, the data speak more clearly about the contrast than the cause. Hydrogen cyanide clings to the inner regions, while methanol stretches farther out. Even before final numbers are published, this split pattern becomes a focal point of discussion in workshops and virtual meetings. It suggests that the internal structure of 3I Atlas is not uniform, but instead stores molecules in distinct physical states and locations, a trait that might reflect conditions in the disk where it formed, or the slow reshaping that occurred during its interstellar journey. While these radio observations progress, optical and infrared teams continue their parallel work, refining the comet's color, tracking the shape of its tail, and looking for any correlation between visual features and the regions where different gases are most abundant. Small shifts in the brightness profile along the sunward side of the coma seem to align with some of the extended methanol emission, hinting that dust associated with these regions may be carrying or releasing that molecule more efficiently. This crosslink between different kinds of data strengthens the impression that the methanol-rich component is not a measurement artifact, but a real structural aspect of the object. Science news outlets begin to report that first radio spectra from the interstellar comet show an unusual mix of molecules. They highlight that while the same basic species seen in solar system comets are present, their relative proportions may be shifted. The tone remains cautious. It is one thing to note that certain lines are stronger than expected, another to claim a fully new class of comet. Still, the fact that such differences appear at all is already informative. It shows that other planetary systems can assemble icy bodies with chemical inventories that do not simply copy the recipes found around the Sun. As more observing windows come and go, the trend in the methanol features persists. Lines associated with this molecule remain prominent across different distances and changing activity levels. The stage is set for a more quantitative analysis that will place 3I Atlas among known comets on a plot of methanol abundance versus other key species. When those comparisons are finally made, they will show just how far this interstellar visitor sits from the familiar cluster of solar system objects and how strongly its chemistry points toward a distinct origin. For now, the message emerging from the millimeter and radio campaign is clear enough to guide the next steps. This comet is rich in gas, active over a wide range of distances, and already hinting that one simple organic molecule may be present in unusual abundance. The question shifts from whether methanol is enhanced to how far beyond the familiar range it extends, and what that says about the conditions in the distant unseen disk where 3I Atlas first formed. As analysis advances and more data from the Atacama Large Millimeter Submillimeter Array and supporting facilities arrive, the informal suspicion that 3I Atlas is methanol-rich begins to solidify into a quantitative result. Teams working independently adopt standard radiative transfer models that convert line strengths into molecular abundances, taking into account the temperature and density of the coma gas, the rates at which molecules are excited and de-excited by collisions and radiation, and the geometry of the expanding flow. They compare the methanol lines against those of water-related species and other common volatiles, using a framework built over many years from solar system comets. In those local comets, methanol typically occupies a modest and fairly stable fraction of the volatile budget. It is present, sometimes enhanced, but usually falls within a band that modelers know well. For 3I Atlas, the numbers that emerge from the FITs refuse to sit in that familiar band. Even after conservative assumptions, the inferred methanol abundance relative to water lies several times above the median values of well-studied solar system comets. When the most cautious error bars are applied, the interstellar comet still occupies the upper edge of the known distribution and may plausibly exceed it. Analysts run cross-checks using different transitions of methanol, each with its own sensitivity to temperature and density. They perform subsets of the fit that exclude potentially blended lines and rerun the pipeline under varied conditions. The outcome continues to point in the same direction. Within the normal scatter of such measurements, 3I Atlas appears to be genuinely methanol-rich. For those who have followed comet chemistry for decades, this is not just another data point, but a shift in the picture of what an icy body from another system can contain. The spatial maps strengthen this conclusion. When astronomers reconstruct two-dimensional emission images for different molecules, they see that methanol does not simply mirror the pattern of water or hydrogen cyanide. Hydrogen cyanide remains tightly concentrated near the inner coma, dropping off steeply with radius, and suggesting a source tied closely to direct sublimation from the nucleus surface or from grains that disintegrate very near it. Methanol, in contrast, spreads more widely. Its emission profile is flatter, remaining strong out to larger distances before gradually fading into the background. This behavior hints that a significant fraction of methanol is being carried away in or on dust grains that survive farther from the nucleus before releasing their cargo. Another contribution may come from chemical processes in the coma itself, where sunlight and energetic particles break apart more complex organic material embedded in the dust-freeing methanol as a secondary product. To probe this idea, some teams examine how methanol emission varies with time as the comet rotates. If the molecule were produced solely by direct sublimation from a few localized patches on the surface, one might expect sharp periodic variations tied to the spin period. Instead, while there are fluctuations, they are smoother and more extended than those of hydrogen cyanide. This pattern is more consistent with a mixture of sources, including an extended population of icy grains whose behavior averages out rotational effects. High-resolution optical images carefully processed to enhance faint structures reveal features that seem to support this view. In addition to a general diffuse coma, there are narrow, slightly curved jets that appear and fade over timescales consistent with the rotation period inferred from brightness variations. Some of these jets correlate with regions where the methanol emission is particularly strong, as seen in overlapping maps from the millimeter array. Others align more closely with enhancements in dust continuum emission, suggesting that streams of dust and gas leaving specific areas on the nucleus may carry different proportions of volatile species. The combined data paint a picture of a nucleus that is not compositionally uniform, but instead contains zones with varying mixtures of ices and dust, some especially rich in methanol-bearing material. In the background, the slightly redder than average color of the comet measured in different optical and near-infrared bands adds another layer. Redder colors in cometary surfaces and dust are often linked with complex organic rich coatings formed by long-term irradiation of simple ices. In 3I Atlas, the association of a redder tone with a methanol-rich inventory encourages the idea that the comet has experienced extended exposure to cosmic rays and ultraviolet light in interstellar space, building up organic residues and perhaps altering the balance of its volatile content. Under this view, methanol may have been both produced and preserved by processes that differ from those acting on comets that spent most of their lives in the shielded regions of the solar system's distant cloud. As the abundance results cohere, teams start to place 3I Atlas on comparative plots that gather decades of comet data. On charts where methanol abundance relative to water is plotted against proxies for formation region or dynamical class solar system comets, cluster in broad but recognizable groups. Some families thought to originate in the distant outer disk show slightly higher methanol levels than those believed to form closer in, but the overall spread is limited. When the interstellar comet is added, its point lies offset from the main clusters pushing toward or beyond the upper envelope of methanol content. The uncertainties are still visible, but the trend is hard to ignore. This object either formed in an environment particularly efficient at building methanol, or has held on to that molecule in a way that most local comets have not. News releases from observatories begin to highlight this result. They describe in simple terms an interstellar comet whose gas envelope is unusually rich in methanol, a basic organic molecule that plays a role in many chemical pathways. They stress that methanol itself is not a biological molecule, but a step in sequences that can produce more complex compounds. Popular science articles pick up the theme presenting 3I Atlas as carrying an outsized share of one of the building blocks associated with prebiotic chemistry. The tone is measured, but engaged. Reporters explain that while comets in the solar system also contain methanol, the interstellar visitor appears to carry proportionally more, hinting that the chemistry of its birth environment around another star followed a different path. Inside the scientific community, attention turns to what this methanol spike implies about the conditions in that distant environment. Methanol in comets is thought to form mainly on the surfaces of dust grains, in cold regions where carbon monoxide and hydrogen atoms can combine on icy mantles. The efficiency of this process depends on temperature, radiation field, and the availability of reactants. A high methanol abundance could therefore mark a region of a protoplanetary disk that was especially rich in carbon monoxide ice and remained cold enough for this surface chemistry to proceed over long timescales. Alternatively, it might reflect a history in which the comet's building blocks were repeatedly cycled through zones of varying temperature, partially processed, and then refrozen in patterns not common in the early solar system. Others consider whether internal processes within the comet, such as heating from decay of short-lived radioactive isotopes or interactions between water and iron-bearing minerals, could have produced extra methanol after formation. If such processes occurred in a body that later spent long ages in interstellar space, they might leave a layered structure in which methanol-rich zones are buried within more complex interiors. The extended methanol emission in the present coma could then trace the gradual excavation of these zones as sunlight strips away successive layers. At this stage, the data do not allow a single preferred scenario. Each proposed pathway must be tested against both the abundance measurements and the spatial distribution of methanol and other species. What is clear is that the unusual prominence of this molecule in an interstellar comet extends the range of known cometary chemistries and shows that planetary systems around other stars can assemble icy bodies with volatile inventories that differ in significant ways from those formed around the Sun. This conclusion feeds into broader questions about how common certain chemical starting points for complexity might be across the galaxy. If one interstellar comet passing through the solar system happens to be methanol-rich, is it an outlier, or does it represent a broader population of objects shaped by similar conditions? Survey programs designed to detect interstellar visitors are still young, and the sample is small. For now, 3I Atlas stands as a vivid example of how a single object can reveal a previously unobserved corner of the chemical landscape. Its methanol spike is not just a numerical curiosity. It is a signpost pointing toward regions of other star systems where cold, dense, and chemically active ices may be common regions that current telescopes can only infer indirectly. As the comet continues along its hyperbolic path, the emphasis of the campaign begins to shift. Having established the presence and extent of its methanol-rich coma, astronomers turn to the next layer of investigation, looking not only at the amounts of key molecules, but at how they behave differently from one another in space and time. Out of this comparison will emerge the picture of a stratified, evolving interior whose complexity mirrors that of the environment where it first took shape. As the methanol analysis matures, attention turns to the way this molecule behaves alongside hydrogen cyanide, another simple but important component of cometary gas. Both are organic in the broad chemical sense, both appear in many solar system comets, and both are of interest as potential stepping stones toward more complex molecules. Yet in 3I Atlas, they refuse to follow the same rules. Astronomers begin to speak not just about abundances, but about stories written in space, traced by how these two species occupy and move through the coma. High-resolution maps from the millimeter array show hydrogen cyanide in a tight knot centered on the position of the nucleus. Its emission peaks sharply at the core and drops away quickly, with distance indicating that most of it is being released very close to the solid body. This pattern matches expectations for a volatile that sublimates directly from exposed ice as the surface warms. When gas models are applied, assuming a roughly spherical outflow from the nucleus, the hydrogen cyanide fits well. It behaves like a trace component, riding along with water vapor and other primary gases, its density declining in a smooth, predictable way as it expands and thins into space. Methanol refuses this simplicity. Its emission is strong near the nucleus, but remains significant much farther out, filling an extended region of the coma. The radial profile is flatter, and in some directions, secondary peaks appear at distances where hydrogen cyanide is already faint. This suggests that not all methanol is born at the surface. Some must be created or liberated in the coma itself, or travel outward in solid form on grains that survive until they reach those distances before releasing their load. To clarify the picture, teams, compare line profiles at different offsets from the nucleus. Hydrogen cyanide lines near the center are narrow and centered close to the comet's bulk velocity, broadening slightly as one moves outward, in a way consistent with thermal spreading and gentle acceleration by gas flow. Methanol lines show more structure. In some regions, they are broader than expected, with subtle asymmetries, hinting at contributions from multiple velocity components. These may trace jets where gas and dust stream out faster along certain directions, or they may mark regions where dust grains loaded with methanol are being pushed and dispersed by solar radiation and gas drag. Photometric monitoring supports this view. As brightness variations reveal the rotation of the nucleus, the hydrogen cyanide signal modulates in a pattern that fits a set of active patches on the surface, turning into and out of sunlight. The variations are noticeable, but constrained, indicating that although some areas release more gas than others, the overall hydrogen cyanide source is fairly compact. Methanol variations are smoother and show phase shifts relative to hydrogen cyanide, as if the peaks in methanol emission lag the surface rotation. That lag is natural if a substantial fraction of methanol comes from grains that need time to drift away from the nucleus and warm before they release gas. Under this interpretation, hydrogen cyanide directly traces the near-surface ice layers, while methanol partly traces a population of icy fragments and dust grains transporting material outward. The implication is that these two molecules belong to different physical reservoirs within the comet. Hydrogen cyanide lives close to the surface, perhaps in a relatively uniform layer, while methanol is locked both in shallower and deeper zones, and within complex organics on grains that are liberated more chaotically. Optical images give further hints. When astronomers enhance the contrast of deep exposures, they see narrow jets and fans emerging from the coma. Some aligned with the direction of the sun, others offset in ways that point to the rotation axis of the nucleus. Certain jets appear bright in dust continuum and match the directions where methanol maps show extended emission, while hydrogen cyanide remains more centrally bound. This reinforces the idea that methanol-rich material is carried in dust structures that persist as they arc away. The picture that emerges is of a nucleus with patchy stratified layers. Some patches expose ice mixtures where hydrogen cyanide is abundant and methanol is present but not dominant. Others include pockets or veins where methanol-rich ices and organics are concentrated. As sunlight warms these areas, they emit dust grains coated with complex material. In interplanetary space, the grains crack, sputter, and erode under ultraviolet light and thermal stress, releasing methanol across a broad volume. Hydrogen cyanide, more tightly tied to the immediate ice surface, does not follow them. Modelers of comet interiors use this behavior as a set of constraints. They construct simple layered models in which a crust of processed material overlies zones of different original composition, inherited from the regions where the comet's building blocks formed in its home star's disk. In some versions, the outermost layer is strongly altered by interstellar cosmic rays during the comet's long voyage between stars, creating complex organics that preserve methanol and related species. Beneath that lies a less processed layer, more representative of the original ice mixture, where hydrogen cyanide and other volatiles are stored in a pattern closer to that of solar system comets. When activity starts, the outer layer sheds dust rich in organics and methanol, while the underlying ice releases more typical gas. Over time, as layers are stripped away, the balance of the coma changes. 3I Atlas is observed during only a limited segment of this evolution, but the bias toward extended methanol suggests that the outer altered regions still contribute strongly. Interstellar processing provides a natural framework for this. During its long journey through space between stars, the comet has been exposed to a constant flux of high-energy particles. Laboratory experiments with analog ices show that such irradiation can both destroy and create molecules, breaking simple species apart and recombining them into more complex arrangements. Methanol is one of the products that can be generated in these conditions, especially when carbon monoxide-rich ices are present. If the upper layers of 3I Atlas have been repeatedly bombarded and reworked, they may have accumulated significant methanol within a matrix of more complex organics. When these layers are later lifted as dust, that methanol becomes a secondary source distinct from the original interior ices. At the same time, the close link between hydrogen cyanide and the inner coma signals that not every part of the comet has been heavily altered. Some regions still behave like relatively pristine reservoirs responding directly to solar heating with patterns that resemble those of long-period comets in the solar system. This mix of preserved and processed zones is important because it suggests that 3I Atlas records both the conditions of its formation region and the history of its passage through interstellar space. On the observational side, astronomers exploit the contrast between the two molecules to refine measurements of the comet's rotation and jet geometry. By tracking how the compact hydrogen cyanide source moves with respect to the inner dust structures, they can infer the orientation of the spin axis. Mapping the extended methanol distribution over time then reveals how jets evolve as different surface areas come under the sun's illumination. This analysis shows that some methanol-rich jets persist over many rotations tied to stable active zones, while others switch on briefly and fade perhaps when small pockets of volatile material are exhausted. The overall effect is a coma whose structure is more irregular and time variable than that of many solar system comets, consistent with a nucleus that has spent ages being reshaped by environments unlike the sun's outer cloud. News reports summarize these findings with simple contrasts. One molecule hugs the comet's core, the other spreads wide. One behaves as if it comes straight from near-surface ice, the other seems to arrive in stages carried outward and released over time. In this way, hydrogen cyanide and methanol become convenient markers for two aspects of the comet's nature: its underlying internal structure and the role of long-term processing. Science commentators note that this is more than a descriptive curiosity. It means that by carefully measuring how different molecules occupy the space around an interstellar comet, researchers can reconstruct parts of its geological and chemical history without ever seeing the nucleus directly. For 3I Atlas, that reconstruction points to a body that formed in a chemically active region, rich in carbon-bearing ice, then spent vast periods in interstellar space accumulating a processed skin, and is now being peeled by solar heat in a way that releases one key molecule across a broad volume. As this picture sharpens, the significance of methanol shifts again. It is no longer simply a molecule found in high abundance. It is a tracer of processes that link a distant unseen disk around another star to laboratory experiments and to the evolving coma of a comet passing briefly through the solar system. The contrast with hydrogen cyanide makes that role clear. While both contribute to the overall chemical inventory, their diverging behaviors underline that 3I Atlas is not a uniform lump of ice and dust, but a layered dynamic object whose structure reflects multiple environments. This understanding sets the stage for the next questions. If a single interstellar comet can show such complex internal organization and such a strong signature in one prebiotic relevant molecule, what does that imply for the broader population of icy bodies around other stars? And how might these bodies seed planets with reactive material? Those questions will guide the next phase of the investigation as attention turns from mapping present structures to inferring the conditions under which such a comet could have formed in the first place. As the chemical maps sharpen visible and infrared images from large telescopes, add a more intuitive layer to the picture of 3I Atlas. In processed frames, the comet no longer looks like a simple fuzzy point. It shows a compact inner core, a surrounding coma, with subtle gradients and a tail structure that shifts in shape and brightness from night to night as it responds to the changing geometry between the comet, the Sun, and Earth. Against this changing background, small but systematic patterns begin to appear that tie the visible behavior of dust and gas to the methanol-rich regions revealed by radio observations. Photometric campaigns on medium-sized telescopes, many of them robotic, collect long sequences of brightness measurements as the comet rotates. The light curves show a repeating pattern that allows astronomers to refine estimates of the rotation period. Within each cycle, the total brightness of the coma rises and falls, but the shape of the variation is not strictly sinusoidal. Instead, there are sharper peaks and slower declines that suggest jets of dust and gas sweeping through the line of sight. When images taken at carefully chosen times are examined side by side, these jets become clear. They appear as narrow fan-like structures extending from the inner coma in specific directions. Over several rotations, they trace out arcs marking regions on the nucleus where activity is concentrated. The overall color of the comet, as measured by comparing its brightness in different filters, remains slightly redder than the average for solar system comets at similar distances. This redness persists over many observations, even as the viewing geometry changes, indicating that it is a property of the dust and surface material rather than a transient effect. In some frames, the jets themselves appear marginally redder than the surrounding coma, hinting that they may carry dust grains with different surface coatings or size distributions. When these images are compared with maps of methanol emission from the millimeter array, a pattern emerges. Jets that are strongest and most persistent in the optical data tend to align with directions where methanol is particularly enhanced. In effect, the same regions of the nucleus that launch bright dust structures also feed extended methanol-rich gas into the coma. Hydrogen cyanide, by contrast, remains strongly concentrated toward the inner region in the radio maps, with less obvious association to specific jets in the visible. This reinforces the idea that methanol is tied to dust. Rich outflows that are shaped by surface patches with distinctive composition, while hydrogen cyanide behavior is dominated by more evenly distributed near-surface ice. The tail of 3I Atlas adds its own clues. Like all active comets, it shows a primary dust tail pushed away from the sun by radiation pressure, and a fainter gas tail tracing ionized species swept back by the solar wind. For this interstellar visitor, the dust tail exhibits mild but noticeable asymmetries that evolve over time. In some sequences, it appears slightly curved with a kink or jog that seems to precess as the nucleus rotates. Detailed modeling of dust particle dynamics suggests that this wobble is linked to jets with different orientations, turning on and off as active regions on the surface face the sun. Regions that throw off smaller, lighter grains produce components of the tail that respond quickly to changes in radiation pressure, while those that emit heavier grains contribute to a more stable backbone. The slight redness of the tail, combined with its structured shape, supports the view that the dust population includes particles with complex organic coatings built up by long-term irradiation. Interstellar weathering is the natural candidate for this process. While comets that spend most of their time in the distant cloud of the solar system are also exposed to cosmic rays, their environment is shaped by the sun's magnetic field and wind. An object that drifts for tens or hundreds of millions of years in the general interstellar medium instead experiences the constant background of galactic cosmic rays and the passage through clouds of diffuse gas and dust. Laboratory work with simple ice mixtures shows that such exposure can darken and redden surfaces, build carbon-rich residues, and alter the mechanical properties of dust. In 3I Atlas, the combination of a redder overall tone jets that appear redder still and a methanol-rich extended coma suggests that its outer layers have been thoroughly processed in this way. The jets may be tapping into regions where these processed materials are concentrated, releasing both complex dust and methanol carried within or alongside it. Infrared spectra from space-based telescopes add further support. Observations in bands where silicate dust and organic-rich material leave broad features indicate a mixture of grain types. The silicate signatures resemble those seen in many comets, pointing to familiar rocky components, but the continuum and weaker bands suggest an overlying contribution from hydrocarbons and related compounds. The relative proportions vary with time and in some cases appear higher along the directions of the strongest jets. When these data are stacked according to the phase of the comet's rotation, a pattern appears in which certain rotation phases show enhanced organic features. Those phases match the times when optical images show specific jets aimed roughly toward Earth, and when methanol maps highlight extended emission along the same axis. This coordinated behavior points again to a nucleus with chemically and physically distinct sectors. In practical terms, the comet presents as a patchwork of source regions, some dominated by more pristine ice and dust, others by interstellar processed crusts, rich in methanol-carrying organics. When the sun lights one of the latter regions, it drives off a mixture of dust grains and gas that marks the jet both in color and in its molecular fingerprint. Over many rotations, this produces an average coma and tail that are slightly red, but internally structured with hotspots that trace the legacy of the comet's formation and its long journey. Comparisons with well-known solar system comets underline the difference. In historical cases where spacecraft have imaged comet nuclei up close surfaces, often show a mixture of smooth plains, pits, and layered cliffs with activity tied to discrete vents. Color variations exist, but are usually subtle, and while some comets are redder than others, their overall methanol abundance tends to fall within familiar bounds. 3I Atlas shares the basic pattern of jets and rotating hotspots, but the combination of higher relative methanol, persistent reddening, and strongly structured extended emission places it at one end of the range. It looks like a member of the comet family shaped by a different weathering regime and perhaps starting from a different initial mix. Science news stories frame this in accessible terms. They report that the interstellar comet carries a dust tail slightly redder than usual, with jets that change as it spins, and that align with regions where an organic molecule methanol is particularly abundant. They explain that the tail appears to wobble because the nucleus is rotating and because different active areas come into view, each launching its own stream of dust. By tying these visible changes to the deeper chemical maps, the reports convey that astronomers are not just watching a pretty object move across the sky. They are reading a record of how ice rock and organic material behave under conditions that differ from those in the outer solar system. Within the research community, these findings feed back into ideas about how interstellar comets might serve as probes of the wider galaxy. 3I Atlas shows that the combined effects of formation in a cold chemically active disk and later processing in interstellar space can produce a nucleus whose dust and gas carry signatures of both histories. Its tail structure, color, and jet behavior are part of that signature, as much as its methanol abundance and hydrogen cyanide profile. The comet becomes a case study in how surface features and rotational dynamics reflect deeper compositional differences, and in how modest, carefully measured departures from the norm can reveal that the space beyond the sun is seeded with icy bodies shaped by a broad range of conditions. The next logical step is to ask how such conditions arise in the disks around other stars and what they mean for the chemistry of forming planets. That question will lead investigators from the detailed maps of this single comet back out to surveys of young stellar systems and to models of ice chemistry in alien environments, weaving together local observation and distant inference into a broader picture. In that picture, 3I Atlas is both a visitor and a messenger, carrying in its wobbling tail and patchy jets, information that cannot yet be obtained in any other way. With the methanol-rich coma of 3I Atlas now firmly established, attention turns outward and backward away from the present behavior of the comet and toward the environment where it first formed. Methanol is simple in structure, but demanding in its requirements. In most models of star and planet formation, it does not appear in large amounts unless ice-covered dust grains spend long periods in very cold, dense regions where carbon monoxide freezes out and hydrogen atoms can attach to it step by step. The interstellar comet therefore points to a birthplace shaped by specific conditions, low temperatures, abundant carbon-bearing gas, and enough time for slow surface reactions to reshape the chemistry of the surrounding ice. To understand what that birthplace might have looked like, astronomers draw on observations of young stars and their disks made with the same millimeter arrays and infrared observatories used on the comet itself. High-resolution images of protostars wrapped in envelopes of gas and dust show rings and clumps, where molecules like carbon monoxide, water, and methanol change phase. In the cold outer parts of these structures, carbon monoxide leaves the gas and sticks to grains, building up icy mantles. Laboratory experiments in which analog grains are cooled to similar temperatures and exposed to beams of hydrogen atoms and ultraviolet light demonstrate that under these conditions, carbon monoxide can slowly convert into methanol and related species. When telescopes measure the emission from these ices and gases, they often find that methanol is concentrated in specific bands or layers, tracing out what researchers call snow lines and chemical fronts within the forming planetary system. In disks around other stars, these patterns are usually inferred at large scales. 3. I-Atlas offers something different, a piece of such a disk condensed into a solid body and delivered across interstellar space. The unusually high methanol abundance suggests that the grains that came together to form this comet spent much of their time in a region of the disk where carbon monoxide, ice, and hydrogen were both plentiful and cold enough for reactions to proceed efficiently. Perhaps the material was parked beyond a carbon monoxide snowline for a long period, cycling slowly between slightly warmer and slightly cooler zones as turbulence and radial drift moved grains around. Each passage through the coldest zones would add new layers of methanol, rich ice building up a mantle, with a composition distinct from that of regions closer to the star or deeper in the disk midplane. Models of young disks offer several ways to realize such a scenario. In one picture, the comet formed beyond a wide cold ring where the disk temperature fell well below the point where carbon monoxide freezes. In that ring, grains would be coated in mixed ices dominated by carbon monoxide and water. Over hundreds of thousands of years, repeated exposure to low-level ultraviolet radiation from the young star and to cosmic rays from the surrounding space would drive surface chemistry that favors the creation of methanol. If planetesimals formed there, they would inherit this methanol-rich profile. In an alternative picture, the material that became 3I-Atlas migrated outward after first forming closer in. As it moved outward, it would repeatedly cross chemical boundaries, accumulating layers of different ices on its surface. Some layers would be relatively water-rich, others carbon monoxide-rich. The interfaces between these layers would be prime sites for the formation of methanol when the right combinations of temperature and radiation were present. Over time, the body could build a stratified interior in which methanol is concentrated in particular shells or pockets. Later, as internal heat leaked away and the body cooled, these structures would freeze in place, waiting to be revealed when the comet approached a new star. Observations of disks with the Atacama Array lend support to the idea that such complex thermal and chemical structures are common. Images in bands tracing a variety of molecules show rings and gaps where conditions change rapidly with distance from the star. Some disks display bright methanol emission in specific rings, hinting that those regions are especially favorable for its formation. In a sense, each ring is a potential nursery for methanol-rich comets. 3. I-Atlas with its elevated methanol content might be a fragment from one such band that was later ejected during the gravitational reshaping of its home system. The ejection itself would likely come later in the story after giant planets or massive cores had formed and begun to scatter smaller bodies. Studies of planetary dynamics show that when large planets migrate or interact, they can hurl comets out of their native systems, feeding a population of interstellar wanderers. If these ejected bodies carry the chemical signatures of the regions where they formed, then an object like 3I-Atlas is both a tracer of disk chemistry and a witness to a period of dynamical instability. Its methanol spike would encode the former, while its hyperbolic path through the solar system reflects the latter. The role of interstellar processing cannot be ignored either. Once an icy body leaves the protective envelope of its home star and drifts into the wider galaxy, it is bathed in a different radiation environment. Galactic cosmic rays and diffuse ultraviolet fields act over vast timescales, slowly altering the upper layers of the ice. Laboratory analogs show that under such bombardment, carbon monoxide-rich ices can be partially converted into methanol and more complex organics. If 3I-Atlas started with an elevated but not extreme methanol content, its long exposure in interstellar space may have enhanced that fraction further, especially in its outermost layers. In this view, the comet is a hybrid product. Its interior reflects the cold chemistry of a young disk, while its surface layers record the secondary processing of the interstellar medium. The observational evidence from the comet supports such a layered picture. The contrast between compact hydrogen cyanide and extended methanol, the redder jets, and the structure of the dust tail all indicate that processed organic rich material plays a major role in the current activity. Yet the presence of familiar volatile ratios in the inner coma suggests that deeper layers still remember their original disk environment. Disk observations of distant stars, comet measurements in the solar system laboratory experiments, and interstellar chemistry models thus converge on a consistent framework. Methanol-rich ices form naturally in cold carbon monoxide-rich zones of planetary birthplaces, and can be further modified as they travel between stars. 3I Atlas fits into this framework but occupies a part of it that could not be probed before. Its chemistry is a point on a diagram that connects specific disk conditions to the later delivery of complex molecules to planetary surfaces. That connection leads to speculation about the implications for prebiotic environments. In standard scenarios, comets and icy planetesimals deliver water and organic compounds to young planets. If some planetary systems routinely produce methanol-rich comets, the early chemical environment on their planets might differ in significant ways from that on Earth. Methanol can act as a feedstock in pathways that generate more complex organics, when exposed to energy sources such as ultraviolet light electrical discharges or geothermal heat. A planet bombarded by a higher proportion of methanol-carrying impactors may experience a different balance of prebiotic reactions in its oceans, lakes, and crustal fractures. None of this implies that life follows automatically from methanol. The comet does not prove that its home system hosts biology. It does, however, broaden the range of initial conditions that can seed planets with reactive material. The presence of a methanol-rich interstellar comet in the limited sample detected so far suggests that such bodies are not vanishingly rare. Surveys of young disks already hint that cold carbon-rich rings are common features. When their products are scattered, they could fill the galaxy with travelers like 3I Atlas, each carrying its own mixture of ices and organics. For now, this remains an inference built on a single well-characterized case and a growing but still partial set of observations of distant disks. Future interstellar comets might show different chemical emphases, perhaps enriched in other molecules that trace alternative pathways. Some may resemble solar system comets more closely. Others may be even more extreme than 3I Atlas. The key point revealed by this object is that the galaxy does not follow a single recipe when it assembles icy bodies. Instead, it offers a range of chemical kitchens, each with its own temperatures, ingredients, and timescales. 3. I-Atlas emerges from one where methanol plays an unusually central role, and its passage through the solar system lets that role be measured in detail. In this sense, the comet is more than a curiosity. It is a data-rich sample drawn from a specific kind of planetary nursery, one that can now be matched against theoretical models and remote observations. The match is not yet perfect. There are still gaps between what disk images show and what the comet's coma reveals. Those gaps form the space where new models will grow, linking the cold chemistry on distant grains to the bright structured coma of a single transient visitor. In the wake of the methanol result, the story of 3I Atlas shifts from the chemistry of a single comet to wider questions about how complex molecules arise and move through planetary systems. In press releases and technical briefings, researchers describe methanol and hydrogen cyanide not as signs of life, but as ingredients that can feed more complicated reactions under the right conditions. Methanol, a simple alcohol, and hydrogen cyanide, a reactive nitrogen-bearing compound, both appear in laboratory simulations of prebiotic chemistry, the set of processes that can build larger organic molecules from smaller ones before any biology exists. In experiments that mimic early planetary environments, mixtures of water, methanol, hydrogen cyanide, and other simple species are exposed to ultraviolet light electric discharges or heat. Over time, these mixtures can generate a variety of more complex products, including molecules that resemble the building blocks of sugars and amino acids. The exact pathways are intricate and depend on many parameters, but the broad message is straightforward. When enough reactive carbon, hydrogen, oxygen, and nitrogen-bearing molecules are present, and energy is available, chemistry tends to explore a wide space of possibilities. 3I Atlas now joins this picture as a natural container and transporter of some of these key inputs. The interstellar comet does not exhibit any sign that its chemistry has advanced beyond simple organics. There is no evidence for large biomolecules or organized structures. The spectral signatures detected so far fall within the category of small volatile species and dust grains, coated in complex but disordered material. Yet the high relative abundance of methanol and the measurable presence of hydrogen cyanide mean that if a body with this composition were to impact a young planet with liquid water and energy sources, it would deliver a concentrated package of fuel for further chemistry. Models of the early Earth and other rocky worlds already include contributions from comets and asteroids as suppliers of water and organics. In those models, the flux of impactors over tens of millions of years seeds oceans and crustal environments with a diverse mix of molecules. The precise mix depends on the composition of the impacting bodies. A methanol-rich population of comets would tilt that mix in favor of pathways that make use of alcohols, perhaps altering the balance between different prebiotic routes. 3I Atlas shows that such a population can exist at least in one planetary system. News coverage of the comet leans into this angle, presenting it as an example of how the galaxy might distribute chemical ingredients, rather than as any form of alien signal. Articles explain that methanol and hydrogen cyanide are part of the same toolkit that chemists use when they try to reconstruct plausible steps toward the molecules of life in the laboratory. They emphasize that in nature, these molecules are common, and that their presence in a comet is not surprising in itself. What is unusual here is the proportion. The Interstellar Comet carries methanol at levels that stand out when compared with familiar solar system objects, suggesting that its home environment may favor a different prebiotic balance. Inside the scientific community, this prompts a fresh look at how observatories and missions track molecules linked to prebiotic chemistry. Radio and millimeter surveys of star-forming regions and disks have already cataloged methanol, hydrogen cyanide, formamide, and other relevant species in many systems. Spacecraft that visited comets in the solar system have sampled ices and dust for similar compounds. 3I Atlas adds a bridge between these scales. It is a fragment that condenses the chemistry of a distant disk into a single measurable object and complements the diffuse signals seen in young stellar environments. By comparing its molecular inventory with those remote observations, astronomers can test whether the comet reflects an average patch of its home disk or a particularly methanol-rich niche. If it represents an average, then many comets in that system likely share its composition, and any planets there would have been exposed to a similar pattern of delivery. If it comes from a niche, then it is a rare sample of an extreme environment that might be less common but still important in shaping local chemistry. Either way, the comet demonstrates that planetary systems can vary in how they stock their small bodies with prebiotic-relevant compounds. The presence of both methanol and hydrogen cyanide in 3I Atlas also encourages new theoretical work on how such molecules interact in cometary ices. In cold irradiated mixtures, reaction networks can link simple species in ways that favor certain products. For example, methanol can be broken and rebuilt through sequences that produce more complex alcohols and aldehydes, while hydrogen cyanide can participate in chains that lead toward simple amino acid precursors. Inside an interstellar comet, these processes are limited by low temperatures and by the absence of liquid water, but they can still reshuffle bonds and set up combinations that become reactive once delivered to a warmer environment. Researchers construct models in which grains and larger clumps inside 3I Atlas see cycles of mild heating and cooling during its early history, perhaps as it passed through regions of its home disk with varying illumination. In those cycles, ices can partly melt and refreeze at microscopic scales, concentrating some species and diluting others. The result would be an interior where methanol and hydrogen cyanide are not only present, but locally enriched in pockets. When such pockets are later excavated by solar heating in another system, they may release material with specific ratios that drive certain reactions in the gas and in any water films that can briefly form on dust surfaces. This level of detail goes far beyond what current observations of 3I Atlas can prove, yet it is constrained by what is already known about cold chemistry and by the measured abundance patterns. The interstellar comet thus serves as a boundary condition for models. Any proposed prebiotic pathway that starts from cometary delivery must be compatible with the kinds of mixtures that real comets, including this one, actually carry. On the observational side, missions that sample comets directly gain a new context. Instruments that measured organics on solar system comets now have an interstellar benchmark to compare against, even if only through remote sensing. Future sample return missions, whether to local comets or to interstellar objects if technology allows, will be designed with such comparisons in mind. The science fiction tone of some media treatments reflects this forward-looking aspect. Commentators imagine future laboratories analyzing grains from an interstellar comet under controlled conditions, tracing how methanol hydrogen cyanide and their cousins behave when warmed and mixed with liquid water. In those imagined scenarios, scientists follow reaction chains in real material from another star system, mapping out not only what is possible, but what is likely under specific histories. For now, these visions remain speculative. The current reality is a set of spectra and images that show which small molecules are present and how they are arranged in one transient visitor. Yet even that limited data set changes how researchers think about the distribution of prebiotic potential in the galaxy. If a randomly detected interstellar comet exhibits an elevated level of a key prebiotic relevant molecule, then it is plausible that many stars host belts and clouds of similar bodies. Planets in those systems would experience bombardment by impactors with different average compositions than those that shaped early Earth. Some might receive more methanol and hydrogen cyanide, others more of different species such as formaldehyde or formamide. Each combination would steer the prebiotic landscape in a slightly different direction. In this way, 3I Atlas becomes part of a larger discussion about habitability and the diversity of chemical starting points. Habitability is often framed in terms of temperature, liquid water, and stable orbits. The comet reminds scientists that the input chemistry also matters, and that interstellar comets can offer rare clues about that aspect. It does not answer the question of how often life arises, but it adds one more measured piece to the puzzle by showing that at least one other planetary system has produced a comet with a methanol-rich hydrogen cyanide-bearing interior. The exact implications of that fact will take years of modeling and further observation to understand. For now, the interstellar visitor sits in data archives and news articles as a marker that the galaxy's inventory of small bodies includes objects tuned to support certain prebiotic pathways more strongly than others. As new interstellar comets are discovered, astronomers will look for similar or contrasting patterns, building a statistical view where 3I Atlas is one early important point. The prebiotic story tied to this comet is therefore not a simple line from detection to life, but a branching set of possibilities grounded in concrete measurements. It turns an abstract notion that other star systems might produce prebiotic-rich comets into something more concrete, an actual object passing through the solar system, whose chemistry can be measured and compared. That transition from idea to data is what makes the discovery feel both firmly scientific and slightly like a news item from a future era, in which the galaxy's chemical weather is regularly reported alongside more familiar cosmic events. As the basic chemical and physical picture of 3I Atlas settles, a different thread of investigation runs in parallel, quieter but persistent. Each time an interstellar object passes through the solar system, a small subset of researchers and observers ask whether any part of its behavior hints at something beyond natural processes. For 3I Atlas, this question is framed carefully, not as a claim, but as a test. The object already stands out through its methanol, rich coma-patchy jets, and interstellar history. It is natural to ask whether any of its other properties show patterns that would be difficult to explain with known physics and chemistry. Radio observatories that can search for narrow band signals add dedicated scans of the comet to their schedules. These instruments normally listen for emissions at specific frequencies that could mark artificial transmitters. In the case of 3I Atlas, they tune to bands that are relatively quiet in natural cosmic backgrounds and perform targeted observations as the comet crosses the sky. Data are processed to look for persistent narrow features that track the comet's motion rather than staying fixed on the sky. The resulting reports are straightforward. No such signals are detected above the sensitivity limits of the observing runs. The radio spectrum of the comet is dominated by the broad, blended lines of familiar molecules and by background noise. Within those constraints, there is no sign of coherent transmissions or patterns that would argue for technological activity. Optical and infrared observers join the effort in their own way. They examine high-cadence light curves for unusual modulations that might indicate regular structures or engineered surfaces, such as sharp repeated dimming events or brightness spikes that do not match the expected pattern from a rotating irregular body. For 3I Atlas, the rotational light curve is complex but consistent with a natural nucleus. Variations repeat with the derived spin period, and changes can be explained by jets and surface features, rather than by geometric configurations that would demand carefully aligned panels or arrays. Spectral reflectance data, which show how the comet's surface and dust reflect different wavelengths of light, likewise fall within the broad range known from organic, rich, icy bodies. No sharp, narrow features appear that would point to artificial materials. Radar observations, where possible, are considered as well. In principle, powerful planetary radar systems can bounce signals off nearby comets and asteroids, building crude images of their shapes and surface properties. In practice, not every target is suitable. Distance, size, and observing geometry all play roles. For 3I Atlas, the combination of high speed and trajectory makes detailed radar imaging difficult. Limited experiments are attempted when the geometry allows, but the echoes are weak and noisy. They suggest an irregular, elongated nucleus of a size comparable to medium comets in the solar system, without the sharp edges or flat facets that would raise immediate suspicion. As with the radio searches, the conclusion is that nothing clearly artificial is seen within the limits of current instruments. Rather than closing the topic, these negative results are used to calibrate expectations. They show that 3I Atlas, though chemically unusual, looks and behaves like a natural comet when examined through the lenses commonly used to search for non-natural signatures. Its hyperbolic path can be explained by ejection from a planetary system during gravitational encounters. Its rotation and jets fit models of patchy layered ices responding to sunlight. Its methanol-rich coma, while distinct in proportion, sits within known chemical pathways. Together, these traits build a case that the object is a product of astrophysical processes rather than technology. At the same time, researchers acknowledge the limits of their view. The absence of narrow-band radio signals at a given sensitivity does not rule out all possible transmissions. The lack of obvious artificial geometry in low-resolution optical and radar data does not prove that no smaller structures are present. What it does show is that if any such features exist, they either operate below current detection thresholds or do not reveal themselves in the ways that standard technosignature searches expect. This recognition becomes part of the scientific value of the exercise. By applying search techniques to a real complex object like 3I Atlas, astronomers test their pipelines against a case that is both challenging and representative of the kinds of natural bodies that fill interstellar space. Any future claim of artificial structure or signal from another object will have to stand out against the backdrop of such well-characterized natural examples. Comparisons with earlier interstellar objects highlight this point. The first known visitor raised questions because of its unusual shape and non-gravitational acceleration, leading some to speculate about artificial origins, even as most studies favored exotic but natural explanations. The second visitor, a more conventional comet, helped anchor expectations by showing that at least some interstellar bodies resemble familiar icy wanderers. 3I Atlas adds a third data point. It combines a clear cometary nature with a distinct chemical profile and rich structure, yet still fits comfortably within natural models. In doing so, it further constrains the range of appearances that unambiguously natural interstellar objects can have. These considerations feed into how future surveys and missions are planned. Wide-field telescopes that scan the sky each night refine their criteria for flagging potential interstellar candidates, balancing speed of follow-up with the need to gather enough data to classify objects properly. When an unusual light curve or spectral feature appears, teams can now compare it against the behavior of known interstellar comets, including 3I Atlas, before entertaining more speculative explanations. Instrument teams that design new radio and optical technosignature searches incorporate the lessons of this campaign, adjusting sensitivity goals and strategies based on what was and was not seen. In public communication, this part of the story is presented with a tone of cautious clarity. News outlets report that astronomers have checked the interstellar comet for signs of artificial signals or structures, and have found none. They frame this not as a disappointment, but as part of a systematic effort to test possibilities. The coverage notes that the real surprise of 3I Atlas lies in its chemistry, and in what that chemistry reveals about planetary systems, not in any hint of technology. At the same time, commentators point out that performing these checks on interstellar objects has value even when the outcome is negative. It helps define the boundary between known natural behavior and genuinely anomalous phenomena. It also normalizes the idea that when unusual objects enter the solar system, they will be examined from multiple angles, including those that touch on the search for other civilizations, but that natural explanations must be fully explored and often suffice. Within the research community, the case of 3I Atlas settles into this balanced position. On one side, it stands as a vivid example of how far natural processes can sculpt an interstellar comet, giving it a methanol-rich layered interior and dynamic jets, without invoking anything beyond standard physics and chemistry. On the other, it acts as a test target that shows how current instruments respond to such an object when asked questions about artificiality. The lack of any strong anomalies in those tests becomes a reference point. It says effectively that a comet can be chemically extreme and structurally complex while still occupying the natural category. The wider implication is that truly unusual signals or geometries, if they ever appear, would have to surpass this bar to be taken seriously as possible technosignatures. As the comet continues along its outbound path and fades from easy reach, this part of its story remains open in a different sense. No single object can answer the question of whether technology exists elsewhere. 3I Atlas instead helps to sharpen the tools used to ask that question. It shows that interstellar comets carry rich but natural complexity, and that careful multi-wavelength scrutiny can separate chemical and dynamical surprises from the kinds of patterns that might require more radical interpretations. In doing so, it frames the expectations for the next interstellar visitor whose properties are still unknown. That next object may be more ordinary or even more unusual. Whatever it brings, the experience with 3I Atlas ensures that both natural and extreme explanations will be tested against a clearer background in which the boundaries of natural comet behavior have been pushed outward but remain grounded in data. As 3I Atlas rounds its closest approach to the Sun and begins to climb back out of the inner solar system, the tone of the observing campaign slowly changes. The comet is no longer an approaching mystery, but a receding one, fading in brightness night by night as distance and geometry work against easy measurement. Large telescopes take over more of the load as smaller instruments lose sensitivity. Integration times grow longer, schedules become tighter, and each successful observation feels more like a last glimpse. Yet the scientific urgency does not diminish. For many projects, the outbound leg offers a complementary view to the inbound phase. The comet now moves through a sequence of distances in reverse cooling as it goes, and that cooling can reveal how different molecules switch off or retreat beneath the surface. Teams that have tracked methanol and hydrogen cyanide since before perihelion continue their series looking for changes in abundance ratios and spatial patterns as the energy budget shifts. If extended methanol emission shrinks faster than the compact hydrogen cyanide core, it would confirm that much of the methanol source lies in volatile rich dust that becomes less efficient when activity wanes. If the relative pattern remains stable, it might indicate deeper reservoirs continuing to feed the coma even as the surface cools. Early outbound observations hint that methanol remains prominent longer than many expected, maintaining an elevated fraction even as total gas production drops. This persistence supports models in which layered interiors continue to expose new methanol-rich zones as older ones are stripped away. In parallel, optical campaigns continue to monitor the rotation state of the nucleus. The repeated tug of jets can over time alter a comet's spin period and axis orientation, a process known from previous missions to solar system comets. For 3I Atlas, careful analysis of light curves across inbound and outbound legs reveals small but measurable shifts in the rotation rate. The changes are consistent with torques from asymmetric outgassing, particularly from the methanol-rich jets that dominated part of the inbound activity. In effect, the comet's own activity has gently rewritten its rotational state during its brief visit to the Sun. This detail reinforces the picture of a dynamic evolving body and adds one more constraint to models of its internal structure and surface distribution of active patches. Space agencies use the remaining months of visibility to test ideas for future missions. Although no current spacecraft can intercept 3I Atlas at this stage mission, designers treat its orbit as a case study. They run simulations of fast flyby trajectories that might have been possible if a ready spacecraft had existed at the time of discovery. They test concepts involving high-energy launch vehicles, solar electric propulsion, and advanced solar sail designs that could, in principle, catch up to such a fast-moving target. The results underline the difficulty. Interstellar comets approach with high speeds and steep trajectories, leaving short windows for practical intercepts. Even with aggressive assumptions, missions would require rapid decision-making and flexible hardware. Nevertheless, the exercise pays off in planning documents and studies that propose dedicated interstellar interceptor craft stored in heliocentric orbits and ready to be redirected when the next suitable visitor is found. In technical workshops, 3i Atlas is used as a template for these future designs, with its methanol-rich coma and structured jets providing concrete science goals such missions might chase. Survey telescopes also take lessons from the comet's passage. Facilities that scan the sky each night searching for moving objects assess how early they detected 3i Atlas and how quickly they were able to classify it as interstellar. They identify points in the pipeline where small improvements in software calibration or communication could have yielded an earlier alert. With the Vera-C-Rubin Observatory and other next-generation surveys coming online, expectations are that future interstellar objects will be discovered at greater distances and earlier phases of their inbound paths. That earlier discovery would extend the window for both remote observations and potential missions. In this context, the unusual early activity of 3i Atlas proves helpful. Because its coma switched on far from the Sun, it offered a longer period during which gas and dust could be studied in detail. Future methanol-rich comets, if found even sooner, might allow an even more complete record of how their chemistry evolves from first stirrings to final fading. On the theoretical side, the comet's dataset settles into a role as a benchmark. Models of disk chemistry now include a parameter space point representing a high methanol interstellar processed comet. Simulations of planetary system evolution incorporate populations of such bodies being scattered into interstellar space, carrying signatures of specific formation zones. Studies of prebiotic chemistry on planetary surfaces test scenarios in which impactors with 3i Atlas-like compositions deliver their cargo to oceans' ice shells or subsurface reservoirs. In each case, the comet serves not as a speculative example but as a measured input. It anchors discussions of what sorts of chemical packages planets around other stars might receive. Popular coverage of the comet's departure reflects this combination of closure and opening. Headlines note that the interstellar visitor is fading from view, taking its methanol-rich secrets back into deep space. Articles recap the main findings in brief: a third confirmed interstellar object, a comet, whose gas envelope is unusually rich in methanol, whose jets and tail show the effects of long interstellar weathering, and whose behavior fits natural models even as it expands the known range of comet chemistry. They highlight that no artificial signals were detected, and that the real significance of 3i Atlas lies in what it reveals about the diversity of planetary systems. Science and science fiction-themed outlets in particular dwell on the idea that this was news from another star system, delivered not as a message, but as a physical sample passing through. The sample cannot be captured this time, but it has been scanned and analyzed at a distance with a thoroughness that would have seemed remarkable only a few decades earlier. Within data archives, the comet's observations are organized and preserved. Spectra images and derived products from all major facilities are stored in public repositories tagged, so that future researchers can revisit them with new techniques. Machine learning tools may one day reanalyze the data to tease out subtle features missed in the initial studies. As that prospect is discussed, the transient nature of the object itself stands in contrast to the lasting record of its passage. The comet will exit the region of detailed observability within a few seasons, then gradually fade beyond the reach of all but the largest instruments, and finally slip into complete invisibility. Its trajectory carries it back into the general interstellar medium, where it will continue its slow journey around the galaxy, altered by its brush with the Sun, but still largely intact. On speculative timescales, it may pass through other star-forming regions, perhaps briefly feeling the distant pull of another star, before continuing on. The chance that it will encounter another planetary system closely enough to repeat its current performance is extremely small, but not zero. In that sense, 3I Atlas is a wanderer whose path through the Milky Way includes a single brief crossing of the solar system, during which one technologically active species happened to notice and record its properties. The final months of observation bring no dramatic surprises, and that absence is itself informative. The comet continues to behave in line with the physical picture built over the preceding campaigns. Methanol remains relatively enhanced. Hydrogen cyanide stays tied to the inner coma jets weaken, but follow expected patterns as the energy input declines. No late-stage outburst or fragmentation event disrupts the narrative. Instead, the object demonstrates that a chemically distinctive interstellar comet can complete a solar flyby without catastrophic change, reinforcing the view that such bodies can survive long journeys and brief encounters largely intact. When the last major observatories turn their attention elsewhere, 3I Atlas still exists, but for practical purposes, the story moves into the realm of models, archives, and comparative studies. The interstellar visitor becomes a reference point for papers on comet chemistry, disk evolution, and prebiotic delivery. It appears in review articles and textbooks as an early example of an interstellar comet whose composition was measured in detail. Its methanol spike becomes a familiar feature on plots and diagrams, a data point at the edge of distributions. Yet even as it settles into this role, questions remain open. How typical is 3I Atlas among interstellar comets? Are methanol-rich objects common, or did observers encounter an outlier? Will future visitors show other kinds of chemical extremes, pointing to different formation zones and histories? How do these variations feed into the climates and chemistries of planets that grow in those systems? The answers require a larger sample than current surveys have found. For now, the comet's legacy is to demonstrate that such diversity exists, and that humanity has the tools to detect it when chance brings an interstellar object within reach. As 3I Atlas recedes into the dark, the instruments that tracked it continue to scan the sky. Somewhere ahead, another interstellar body is likely already on its way inward from deep space, unremarked, until survey images catch its slow drift across the stars. When that happens, the experience with this methanol-rich comet will shape the response. Observers will move faster, models will start from a broader baseline, and mission planners will have clearer criteria for when an interception is worth attempting. The next discovery will not erase the significance of 3I Atlas. Instead, it will join it in a growing, still sparse catalog of interstellar messengers, each bringing news not in words, but in the language of ice dust and simple molecules, shaped in places the solar system can never visit directly.